Okay, our discussion on the seismic is on the site investigation technique using the seismic wave technique, which is refraction or reflection. But this when you are able to understand the wave, this technique, you are able to understand the application why you use to understand the ground impact to this earthquake event. Okay, so why the some allocation when the earthquake occurred, we have the huge destruction on the building, but some area is not. So you should understand the ground of this area. So this is an example of the velocity of comparison between P wave and S wave, shear wave and compressive wave in type of material for ground and basalts, for example here. And then based on that S and P wave, you're able to calculate the modulus of rigidity, modulus of Park modulus. If you get that VP or VS of material, you're able to calculate the modulus of the material. Okay. For water, yeah, for example here, the best thing about this wave, S wave, is zero velocity in water or petroleum or in air. So meaning here, if you have if you have saturated material like in our part Raja, so the technique of P waves is sometimes quite difficult to differentiate the soil profile. That's we recommended to use the S wave technique, because you are able to differentiate the influence of water groundwater table on that area. Okay, this P wave, A wave, S wave. And second technique and third technique, which is we can use the electrical resistivity technique. This electrical technique is using the electric technique, which is to measure the resistance of the ground. So in electrical, we know we have voltage, we have current I, and then V over I is resistance. Yeah, this is our, we know from since our form 5. The technique is started by injecting the current on through the pair of electrode, and then the potential electrode will measure the voltage of this. The potential difference is measured between two additional electrodes, means you need 4 electrodes. Okay, then and to calculate the resistivity is based on that formula. So this is a resistance. R resistance is voltage divided by I. I is the current voltage. And then to get the resistivity, this is in ohm. The unit is ohm. But here is resistance. Resistivity is here, equal to resistance times area divided by length, means is ohm meter square divided by meter. So means here is you have to cancel off meter, so the unit of resistivity ohm meter. Okay, per ohm meter. So means you need to have a current electrode, pair of current electrode that you inject current to the ground. Then you are able to measure the potential between these two electrons of the ground. Okay, electric property is shown by ability to transmit ion. This ion is important that bring the electron by the movement ion in electrolyte solution, moist soil, and water bearing rock result that electric conduction. Yeah? The resistivity is measured how strongly a material oppose the flow of electric conduction. So mean here, if we have the resistivity value is depend on the porosity. Since you know current resistivity is measured how strong the material oppose the flow of electric conduction, how strong that the currents flow to this material. So then the flow of the current is based on the ability to transmit the ion. So an ion is normally in the electrolyte, so in solution or in the conductive material or water bearing rocks. So meaning water is very important here. Water means the moisture. Solution in the material is important, influence the resistivity value. So porosity is very important factor that influence the water in the material, as well as degree compression. Pore structure is connection between the pore of material. You can see is filled by the is void that filled by water. Or solutions, okay, type of solution, okay, if water or salt water or fresh water, okay, and degree of saturation, so whether saturated or unsaturated. If clay content, why clay content is important? Because clay, we have a few type of clay. Some clay is keep the moisture higher than the others clay. So it's depend on the clay type, clay content, and also mineralogy. So this is the factor that influence the resistivity. So meaning that here, be careful in interpret the resistivity result. Okay, if you are looking on the, let's say you want to measure resistivity to know the soil profile, is quite dangerous, because in, let's say for example, this is our rocks. You want to look on the soil profile, you want to look on the boundary of soil and rocks here using this technique. Is it possible? Sometimes possible, sometimes not possible because of water. If we have very low groundwater, see our water table here, so mean that here, so all this material is submerged underwater, and then this rock, let's say we have a very fractured rock, and then this rock fractured is filled by water, then just imagine all this material is saturated. So mean that this material is soaked and cause this resistivity value will drop even in rocks. So all this material can show very low resistivity. So therefore here I suggest you think resistivity technique to be adopted. So when you want to use this technique, for what purpose? So for example, you want to find groundwater. Okay, it's fine, because this is the good thing in resistivity is to able to detect where is the moisture, the location that have a very low resistivity, which is related to the moisture. So if we want to find groundwater, it's good using this technique. Or to differentiate fresh water and salt water. So salt water is very the ion is very high concentration of ion compared to the fresh water, so you can able to see the differences in the resistivity value. Okay, so the application normally to use determine the water boundaries, which is underground river, or able to determine sinkhole cavity, or able to determine soil weathering profile. If the groundwater table is very deep, so then you can see then meaning that area is not influenced by water. So this is application of resistivity. Normally it's good for this to check the underground water fractured area. Where is the fractured area in rocks, or to find groundwater in rocks, in fractured rock, or to find freshwater zone or see saltwater intrusion. Yeah. So that is the equipment that we use in this study. And this is ABM thermometer. So we lay the cables. Then okay, we have used 4 cable here. Total length of 4 cable is we have 400 meter, or you can sometimes you can use 800 meter length. It depends on the type of cable. For in the market we have 100 meter length for each cable. Some we have 200 meter length cable. So if you have 200 meter length, maximum length for 4 cable is 800. So 400 you can get 400. So we use electrode, yeah, that we have to punch to the ground. We have the jumper, and then we have a battery. Then this is the data acquisitions logger, data logger, and then yeah, this is the how we arrange the equipment on the field. So we are able to measure the resistivity for each point area. Then after that we can do similar like the resistivity, the seismic resistivity. We able to do this image or tomography, contouring of the value, and then call it tomography. Yeah. So this is how we conduct this test in the field. Yeah. So this technique, look on this. See, this is the electrodes. So this is the jumper. So this is how we test it. Okay. Then so we process it, and then this is the data acquisition process, and then we got the data. It means represent data. That's why our data is like that. So the topography that we get is like this, shape like this, not the whole area. So mean that here the end here, at the end here, the data is not fully deep. So the full depth is on the in the middle. So these two line here is you can get the full depth, or the outer line is only half of the depth. So normally for if we have 400 meter length, using gradient protocol, you're able to get up to 880 meter depth. For in this case is they try to measure up to 7 meter. Yeah, 7 meter. They use up to 40 meter length survey, and then this one for to check the pavement layer. Is any cavities under pavement layer? They study, and then this is they do for groundwater exploration. See, this is they do this in the Gadi water treatment plant. So they do a few line here, and then to define the profile, the depth, or the resistivity distributions. So normally we look on the very low resistivity as a point for drilling. Okay? So if we have this, shows the waters outcome of the study. Or if you want to look on the profile, for example here, we study the abutment soil profile along at the abutment. So you can see the pavement layer. They actually try to investigate, because this abutment have a settlement, quite huge settlement. So this is near the data. Okay, try to look the reason why the settlement occurred this area. Is any cavity and on that area. So you can see this very high resistance here, means quite dry that material, and quite hard. It's normally is pavement. Underneath here is very soft soil, erogenous soil, which is very low resistivity. In this material is submerged underwater. So this groundwater table here. So means if you have a very high water table, means you have low or resistivity value. If you have a solid material, for example granite here, can reach to up to 5,000 ohm meter to 1 million. For example, quartzite between 100 to 2 millions, 20 millions. So why is the range is very huge here? So means here is there the reason is because of water. If that material is underwater, soak underwater, the resistivity will drop dramatically. Yeah? For example, granite here, if underwater, can reduce up maybe to 100. Yeah, for our experience, granite can drop to 100 ohm meter.